going to finish our discussion on parameter efficient fine tuning. We're going to go through and do kind of a quick review first, and then there was some section, a section on coding that I thought we'd do, and then if we have time, we'll also dive into LoRA, which is another application of parameter efficient fine tuning, kind of in a different way. So let's see, share screen then. I think I will do.
Roger, we're getting a bit of popping from your microphone. I don't know if anything you could do on your end.
Well, let me switch. I'll switch over to the microphone, the webcam, see if that's better. How's that?
Yeah, it's a different sound, but it doesn't have the popping at least.
Okay.
It is infinitely better.
Oh, great. Good. Okay. So back to share screen. Go to here. Okay, so this is the original slide deck. We're going to dive through kind of what is fine tuning, some of the paper, original paper. I want to introduce the difference between Adapterhub and the PEFT library from Huggingface. We'll look at a little bit of the code. I was kind of interested in the different implementation styles that they did between the two. And then again, we'll move on to LoRA if we have time. So what is fine tuning? So the idea is you take a large model that's been trained, a lot of effort been put in training it. Now you want to use it for some new application. Often what you'll do is change kind of what the output layers. You'll freeze many of the layers perhaps, and just leave a few that are still trainable. And you'll run through and train a part of the model for whatever the new task might be. And how many layers you do is kind of a, that's a hyperparameter type of thing. The disadvantage of this is that all of the parameters are trained. And so you have a lot of updates, a lot of the optimizer state that you have to manage, et cetera. So with parameter efficient fine tuning, the original proposal was from Neil Hulsby, and they initially would stick these adapter layers in after each of the feed forward layers. And the adapter would have kind of a low rank. It's got a down project to a lower dimensional space, and then up project. That was again in this residual connection, would be then added right after the feed forward output. And this slide, I think we struggled a little bit with last time, but the idea is that the number of parameters can be quite small relative to the overall model. And you could achieve performance comparable to fine tuning all of the layers. So I think this was just a few layers being trained and then up to all the layers. So with a much smaller, what is that, order of magnitude, smaller number of parameters, you could achieve similar performance. Does that make sense? Was there any questions on there? We sound and everything working okay here?
So one question, Roger, would be, what's the difference between fine tuning and transfer learning in terms of the parameters updates?
Yeah, I'm not sure if I can quantify that. A transfer learning is that's typically for another
Domain.
application, and yeah, another domain, yeah. But I think it may be that fine tuning is one way that you can do it. I don't know. Does anybody else have any answer to that question?
I would agree. I think the typical ways that you do transfer learning is you fine tune a pre-trained model. There's probably some other technicalities, other ways you can do transfer learning that I'm forgetting.
Yeah, there's teacher-student model is another way to do transfer learning. So transfer learning is a broad class
of moving information between models, and fine tuning specifically is a either a domain restriction or a domain transfer, and a specific application of that, which again, the best contrast I can come up with is student teacher models, because that's explicitly a form of transfer learning that is not fine tuning.
And in a student teacher, you typically you'd be transferring between architectures, right? Whereas fine tuning, you're reusing the same
That's exactly right.
Yeah, like distillation. So like, for example, when you take a pre-trained ImageNet model and you're doing some vision thing, usually you're putting a new prediction head on the model. In the case of LLMs, usually you don't change the prediction head, you're just simply fine-tuning it on some private data to kind of like, you know, get that little extra bit of performance on your stuff, especially if you have a little bit of proprietary language or something like that. But yeah, the general gist is that if you want to be able to make actual changes to the model, you're going to have to change some of the weights. And traditional fine tuning, you kind of need to change all of them in order to get the best performance. But that's a lot of weights then.
So basically, the one where you have the top layer, a different prediction layer. So essentially, you're doing feature extraction and then transferring those for the prediction. Right? I mean, I think that's probably maybe the technical term. So and then parent teacher, that's called distillation, right? What Sally mentioned. And then fine tuning is just change nothing but maybe top layers for a specific subclass.
Yeah, you could choose, and generally I think is that if you limit the number of layers, the number of parameters that you allow to change when you do fine tuning, you tend to get worse performance. So to get the best performance, you kind of just need to let all the weights and all the layers change, or almost all. And then if it's a very big model, then of course that's very expensive.
Thank you.
So in these examples, I guess these are language. I don't know what the correct term to use here is, because the domain would be, it's still the language is still the output, right? So we're really not, in these language model examples that we're going to go through, we're not changing the output layer. We're changing the task. So I don't know if that's...
Yeah, I don't think it has to be a different problem in order for it to be fine tuning. Again,
you
know, you could just be like, oh, I do legal stuff. So you want to fine tune it with some of that extra legal jargon or medical or automotive parts, whatever. But just something where you're like, it's going to perform a little better if I give it, you know, a bunch of training text that includes the words that are specific to my particular business.
Right. Okay. Let's keep going then. This is just a language, a benchmark that was being used for measuring this. I'm going to skip through some of these or breeze through them real quick. So there's different types of adapters. Once this idea was proposed, there's different types of adapters that were created. Also, as part of the original, this Pfeiffer 2020, they proposed this idea of an adapter hub, which is that once we all have a copy of the base model, we can now exchange these adapters that are, you know, very lightweight, you know, fraction of the number of parameters. And the idea is you can exchange those for specific tasks. So kind of this hub idea. Okay, so LoRA was one of the models that was proposed. It's similar to the original adapter. It's still fitting into the adapter category, adapter hub, but instead of making it something that's in line with the feed-forward network, it's something that's set aside in parallel. So concurrent with the matrix, in this case, we're showing it on the QKV matrix. They're run in parallel to that. Another one that we'll dive into is going to be prefix tuning. This isn't really a good picture. We'll have a better picture of prefix tuning and how that works later on. And this is where I want to jump over to the slide deck. Okay, so this is the prefix prompt and p-tuning. These are done a little bit different than the LoRA, where they're actually kind of going in and changing the weights. In this case, instead of changing the weights, we're adding some additional context to the transformer. And the context then is used to kind of steer the predictions in a particular direction for particular tasks. I'm going to use Ted's slides here for how we build this up. So the original paper, this was the picture of the original transformer with the encoder on one side and then the decoder in the other. You've got input embeddings and then output projection here. There's attention followed by feed forward. These units are replicated multiple times. As you'll see with Ted's updates, most of the models we're talking about nowadays are decoder only. So you get rid of the encoder and you get rid of I'm not sure what that attention is called, but the cross attention back to the encoder. And now it's mostly attention just within the decoder. We've all seen this before, so it should be pretty quick. There's cleaning up that diagram, and then this rearranging it so that we can see that actually it's kind of the residual stream is the interesting part. And we've got these various things that along the way will modify the residual stream: attention, self, and cross attention, and then feed forward networks. Each token that is entered into the sequence of tokens will pass through these weights. So this is depicting kind of an entire sequence right here. All of them feed in. They're predicting the probabilities of next probability, or the probability of the next token at each point. And let's see, shrink that down, add multiple layers because these are many layers deep. And what we're going to do is, in this prefix, I'm going to just focus on the first layer, although for most of it, for the prefix, it actually applies to all the layers. But to start with, we'll just look at the first layer. And what we're going to look at is this attention block in these layers. So this is kind of zooming in on that orange attention block with some internal representations. Does that make sense, first of all? Okay, no questions. Can somebody speak up so I know that we're still here?
Yes.
Okay.
Yeah,
good.
we're giving you thumbs ups.
Okay, yeah, good. Okay, so these are the attention blocks on the first layer. I'm going to remove the orange so that we can look at the details inside. So what's happening on these layers is that the tokens each of the tokens is coming in. It's being multiplied by these weight matrices to form keys and values. And then right now we're only focusing on the prediction of the last token. So I'm only showing the query from the very last token in the sequence. But it again is a multiplication of the input token, actually the embedding of the input token, times the weight matrix. Once you get these QKV values, you then do a dot product matrix multiply between the query and each of the keys. So query times the key, and you do that for all of the ones in the sequence. That produces a scalar for each one of these, predicting, and that kind of measures the similarity between the query and the key. So the query and the key of the first token, between the query from the last token to, let's say, the first token, second token, third token, etc. So once you do that, we run that through a softmax. That'll give you a probability distribution for each of those. So the sum will all add up to 1. And we take those scores and multiply them times the value associated with each of the tokens. So the ones where the query and key match more closely, let's say right here, the query and the key match more closely, so that the output, the score was 0.5. That value will be heavily weighted in this sum. So we'll sum up all of the scores, scalar multiply times the values, add all those up, and that's the amount, the value that we will then add in to our residual stream. Okay, does that make sense? This was a place that we kind of struggled with last time, so I wanted to have a little bit more picture to work with.
So one question that I'm trying to understand, and yes, this makes perfect sense. So residual stream also has a direct path, right? Where none of these values may be overwritten. So is that something, there's another gate up front, or like this X4 probably going directly to Z4, right?
Is it, so are you asking the question, so we were just diving what goes on inside this little orange box, right?
That's correct, yes. So that is where it will come out on that little plus, yeah, where you're
right. It'll come,
yeah.
Right, it'll come out here. It'll do an update to the residual stream before sending it on to the next feed forward network, etc. Does that make sense? Does that answer the question?
It does, it does. My question would be that in all likelihood, there's always some transformation to the value that happens for each of those heads, for each of those tokens, because if we go back to that other diagram, so keeping this diagram in mind, so even if, let's say, one of those is almost 1.999, let's say K3 cube 3 results in V3 becoming 0.999, and that's the one that we need to send along. So our original X3 goes into Z4 as V3, but not the direct V3, whatever V3 is as part of the WV transformation. So in some sense, we are maybe not doing a direct pass through here. We are still transforming it in that attention head. And I was wondering that there are times when you might want to just pass through without transforming it at all. And if there was a path to do that as well.
Well, that would just be a WV of identity, right? An identity matrix for WV would do that.
It will, except that WV is a common matrix across all tokens for all inputs.
Right. So one of the heads might be the raw token unmodified at that location.
Okay. Yeah, that might make sense.
Yeah, the other heads would do something else to them, maybe extract, the color of the token or whatever, the tone of the token. But I think we saw where there was some heads on the first layer that were just doing a copy.
Thank you, Roger.
Sure. Okay. So one thing back when we were talking about this last time, I think there was also some confusion.
Hey, Roger?
Yeah.
Can you back up on that comment about the copy?
Yeah.
So if we wanted to make another copy, I guess the way to do that would be to set the value just to a hard 1? Everybody 0 except 1 in this diagram?
Yeah.
The scores, I'm sorry.
So if this guy, for instance, is saying noun, he's looking for a noun, and we have one of the attention heads, because I'm only showing one attention head here, right? There's actually multiple.
Sure.
Actually, it may be that these are meant to depict each attention head, but whatever. If this was to say noun, and one of the attention heads, the query or the key value was noun, so that those two matched. So if the key value is noun, but the value is identity, the weight matrix for the value is identity. then it'd say, I want to know about a noun. It would match, and this is the only one, let's say, that came up as noun. And the value that would be added to the stream then would be whatever that token was. Does that make sense?
Yeah.
And by the way, I'm just hypothesizing this. I'm tying this into some of the discussions that we had last week about the circuits.
Mm-hmm. Well, it makes sense. It makes sense, right? If from a circuit view, that's like a hardwire versus having a resistor in place or something like that.
Right. A conditional hardwire, it'll switch, right?
Right. Yeah, if we want to go back to electronics 101,
Right.
Like that. All right, thank you very much.
You're welcome. Any other questions? Are we good? Okay, so let's see, this one, I think what I was wanting to depict here. So mathematically, think of it as all of these keys and values. When we are at this point and we are predicting the next token following this sequence, mathematically, we're looking at all these key values are the product of the input token and the weight matrix for that. In practice, when we are generating a sequence and we're generating one token at a time, what we would do is, we'd have 4 in the sequence, we'd generate a probability distribution for the 5th token, we'd sample that and have a 5th token in, and we'd do it again. Mathematically, it would be exactly the same. You'd have all these matrix multiplies, the input tokens times the weights gives you the keys and values, et cetera, all the way up the stack. But in practice, there's an optimization that says, well, actually for the prior tokens, I've already been through this process. I've already multiplied their input tokens times the weight matrices to get the keys and values. So rather than doing that calculation again, I instead can just cache those values, and I can do the exact same thing I did before, but I don't have the weight matrix multiply except for the new token, the one that I just sampled, and I'm adding that on to the end of the sequence. So we don't have any lines. We don't have the other tokens. We just have cached values. Does that make sense? Does that help clarify that optimization?
It does, though I'm sure the implementation gets a little complex because you're basically pipelining your token evaluation by.
Yeah, it's when you're this optimization is helpful when you're generating one token at a time, predicting the next token, et cetera, over and over to generate a long sequence.
Yeah, I mean, I was just thinking from the practical point of view, what does it save? I mean, does it? Anyway, that's not the topic for today, but I was just thinking about that.
Yeah, the quick answer is it just saves this multiply. You just have this prior, because the K1 in this picture and the K1 in this picture is the same. It didn't change, assuming the sequences.
So it saves energy. Sorry, go ahead, Jerry. Yeah,
Could be a fairly non-trivial sort of operation, right?
Yeah.
Depending upon the size of what those matrices turn out to be.
Yep.
You're completely avoiding a fairly,
it's pretty big. It's
yeah,
pretty big.
Yeah, fairly big series of matrix multiplications.
Especially because this sequence is often very long. So it means most of the matrix multiplies you don't have to do because you have the values stored already from a prior pass. Okay, the reason this is kind of interesting here is when we get to prefix tuning, what we are doing is, so I'm showing it, I guess I still have the matrix multiplies here, but we are essentially doing the exact same thing with some stored key and key vectors and value vectors. Okay, they call them virtual entries. Okay, but notice they don't have any tokens associated with them, and there's no matrix multiplies going up to them. They're in kind of that same vector that would be multiplied by Q or multiplied by the scores, but they're not generated from any other calculation. Is that clear? So the thing is, so the question is, well, so where do these come from? And these basically are derived by gradient descent into these values. So they're not constrained. They're, you know, whatever the constraints are on the residual stream, these aren't constrained by that. These can be whatever they need to be to guide the answer, the prediction for the next token in the right direction. You know, these might be, for instance, you know, we want this to be a sarcastic agent and instead of a helpful agent, and these could drive you towards sarcasm on all your predictions. Does that make sense?
It does, Roger. Just one question on that one. So if we have this will be processed for the first token. After that, the same optimization kicks in, right? It's already captured.
In the sense that these guys never have the weight multiplication going in. Like if I was going if I sampled from Z and I now have X5, yeah, I wouldn't be doing these multiplies. I'd be doing one more multiply out here for X5. And when I did a query, the Q vector, when I multiply it by the keys, I'd multiply it by all the keys, including these again.
I take that back. You're right, because the values will feed in from those red
Yep.
prefixes as well.
Yeah. Yeah. So let's see, I think the next slide, an important thing to know about prefix tuning is that this occurs at every layer of the transformer.
Roger, just a minor nit on that.
Yeah.
If I think you're adding up to 1.1, not 1.
Oh, okay. Sorry.
Small math error, but you know, it just threw me for a loop, and I just thought I wanted to make sure it wasn't just me being stupid or something.
Yeah,
like that.
yeah, no, you're right. You're right.
Okay.
That was a cut and paste error. Sorry. Yeah, that should all sum, because of the softmax, those should all sum up to 1. Okay. So wanted again here then point out that it's at each layer that we go along. An interesting thing too, a comment that I saw in one of the blogs, in fact, I need to add that to the presentation, is you can think of this as a query sensitive, a kind of constant addition to each prediction. So these values for any given query will always add the same. It won't necessarily add the same score because it depends how the rest of the sequence happen to be, but the values that would get added are a constant for a given query. So they're kind of viewing it as a bias towards the prediction.
But it wouldn't be that hard, 0.1. It would be the 10% of the total ratio, if I'm understanding that correctly.
Well, actually, I mean, it would depend on how good of a match the other ones were. So if the query matched well with one of these red keys, and none of the other keys matched well with the query, then it would be mostly biased by this prefix.
Ah, okay, makes perfect sense.
So the sequence can affect it, but they were trying to capture it as kind of it's a kind of this constant bias towards the prediction. So
yeah, so an example would be, let's say if you're saying put this in straight line, and if it's sarcasm, it's or don't. You know, the next one would be or don't, or if it wasn't there, then it would be something else.
right.
Yeah, so you said that it's dependent on the query, or is it dependent on the model, the p-tuning prefixes? So for each query, and who decides these vectors?
When I'm saying query, I meant the Q vector.
Oh, okay.
So but how well does the key match the query, the Q vector?
I see that. Okay, and when you said are these fixed as in the actual tokens, or they are passed along as the actual vectors to the model?
So they are passed in. So in here, I've got 3 layers depicted. So we start out with the encoded token. We do the Z layer output of the first layer becomes the input to the next layer. And then this Z would be input to this one, et cetera. So this is a stack of 3 layers here. Each one of these layers would have its own parameter tokens that are that are found through gradient descent. So different ones at each layer, but each time you generate another token, you have those same ones as part of the match of the attention. You can always attend back to those 2 prefixes. Did that answer the question?
It does. I'm just thinking from training point of view. So these, along with the W, V, those weights and all other parameters, these are also the parameters that prefix tuning will now have as part of the model for each of the layers and for each of the heads.
Right. So these would be a separate set of parameters tuned for a specific task. And you could have a model where you change the prefix. The prefix tokens could be sassy, it could be helpful, it could be childlike, whatever. And you just load in the prefix depending on the type of bias you want to make to the predictions, what type of task. Does that make sense?
Okay.
And
it does.
And they're going to be small, relatively small to the overall size of the model. So pretty small number of parameters.
Sounds good.
Okay.
Thank you, Roger.
Okay, so this is prefix tuning. And then there's some variations, 2 more variations to go into that are now kind of related to that. In this case, each layer had its own copy of these virtual tokens. In prompt tuning, they instead add a virtual token instead of, well, a virtual input, I guess I would call it. This is now trainable. It's not coming out of an encoder. It is derived again through gradient descent into this. And I actually don't recall, I drew it as just 1 parameter. It might be there might be multiple that you could do for the prompt tuning. So instead of having, like in here where we did prefix tuning and we had these red ones, which are the parameters that are trained through gradient descent, we had them all the way up. When you go to prompt tuning, instead there'd be just one down at the bottom, and all of the K's and Q's or K's and V's will be derived as it goes up the stack. But there's only one that is trained. The rest are all determined by the matrix multiply. Does that make sense? So it's a lot lighter.
Roger, if I could make a comment, I felt like this one is a little bit more intuitive because let's say you had 4 of them instead of just 1 red box.
Mm-hmm.
Okay. And if those values happen to be the exact same values you would have gotten if you added the words "talk like a pirate" at the beginning.
Yep.
Then you could easily see how those 4 red boxes would downstream affect all of the predicted words because they're numerically exactly identical to as if you used a non-prompt tuning thing and you just inserted 4 tokens to talk like a pirate.
Yep. Yep. I agree with that. The one point is that they are not constrained by the token embedding. So,
that's right.
Yeah, so they can be more expressive than those 4 words might be.
Yeah, I think you can pack more into a single position than you could if it had to come from the embedding. But I'm just saying, conceptually, I have a mental model that
works for that.
Little red box could somehow carry the equivalent of talk like a pirate.
Yeah.
Right, and one benefit of using compact embedding is, let's say, talk like a pirate of a 17th century, like blah, blah, blah. All of that can be captured in one embedding here.
Possibly. And I think they were saying that it generalizes better too. Again, probably because it's not constrained.
All of this is done at training time or post-training, and we're doing this.
So yeah, this would be this is your fine tuning to come up
The
with
fine
this.
tuning the training operation. Okay.
Fine tuning for a specific task, right?
The talk like a pirate task or whatever we want to call
Yeah.
it. Or the,
Yep.
you know, Pirates of the Caribbean ride or whatever, you know.
Yep.
Okay, got it.
You know, Ted, so this, I can understand why this is more intuitive. But if you then took that intuition and said that, well, these are at the beginning of the sequence, so they can only have self-attention. They can't attend to anything prior, which means that as you go up the stack, you can predict the key and values all the way up the stack. So given this, if I had a good prompt tuning, it seems like I could pre-compute all these prefixes values directly.
Yeah,
Right? And then
I
it's
think
the
that's
same
good.
thing.
I think that's a good intuition as to like, you could sort of think of the correspondence between the two different methods.
Yep.
But the other one for me is just sort of an easier starting point because you can just imagine like virtual words, you know, feeding in there.
Yep.
And then to your point, the first one you showed, the prefix tuning, if those red boxes were the exact same red boxes as the talk like a pirate percolating up through the layers, then you're going to get the exact same behavior.
Yep, exactly.
Can these be intermixed? I mean, we've said, you know, we're going to do talk like a pirate, but could you have talk like Samuel L. Jackson, now make Samuel L. Jackson talk like a pirate?
I don't see any reason why not. I haven't tried that. I'm not sure if the libraries support it. But yeah, it seems like you should be able to. It seems like these virtual tokens, you should be able to kind of composite them in. And whether it's down at the bottom as a prompt tuning or up further in the model as prefix tuning, it seemed, my intuition is you could just stack them up.
Yeah, I'm thinking back to that volley. You remember that paper we did a while back?
Mm-hmm.
You know, we had the kind of the voice thing here, and just trying to put this into context where you might use it. And I was thinking, oh, you could kind of, you know, fine tune whatever after you imitated that voice, and then have it, you know, take it someplace else.
Yep.
And that's a good example. So essentially, you know, with the prefix tuning, the previous example, you can potentially have your red tokens there, different tuning for different layers. So in the beginning, you may have talk like a pirate, but towards the end, you may have changed to the voice of Johnny Depp or whatever like that, right? So I mean, voice, if it is language, then there's no voice, but you get the idea. Whereas with the prompt tuning, you can still try that and it may still work, but it is less control compared to prefix tuning. But it's very complex. Prefix tuning is very, very complex. I mean, if you have to try to achieve something like that. Sorry,
all three.
Go ahead.
Yeah, I was going to say these three are all very similar, and I think you can kind of extrapolate the relationship between them. It's kind of some sort of context that's preceding your sequence. The one thing is that I think we're going in reverse expressibility. These are very expressive when you have all these tokens all the way up the stack, right? You have more degrees of freedom there than you do having just one down at the bottom. Okay, the one other variation that you might see is p-tuning, similar to prompt tuning, but instead of generating the token directly through gradient descent, we actually feed in a task name into a LSTM and use that to generate the unconstrained token. So this is even, I don't know, maybe more general, I don't know, but it's another variant anyhow. This one's less intuitive to me. Okay, I'm gonna switch off if we're done with these pictures. Any more questions on these pictures? I'll switch back. Okay.
Hey, Roger, so one comment on this one, the previous one.
Yep.
So your LSTM may actually give you a different embedding every time, which may be more fine-tuned than just a token or a prompt embedding potentially. So you may have more fine-tuned control with P-tuning. Potentially, I don't know, but I'm just thinking out loud.
Using the same type of logic, if I can feed in a task name and an LSTM spits out a value, then I could have derived that same value for that task through gradient descent too. So again,
isn't that fixed after you have trained it and X1 is fixed, but over here you are passing it through another model and then getting a new value?
Yeah, and so that's why I'm saying it might work. It might give you a reasonable X1 for a task name that is similar to something you had before, but not exactly. So it might, my intuition is it might generalize out to other tasks that are somehow similar.
Okay.
Yeah. Okay. So that is the additional pictures. I'm not going to go through this stuff. We went through all this in the last one. I think we went through IA3 also and composition. Okay. So I think this is the place that we got to then, where we were talking about this adapter hub versus Hugging Face. So when I started looking into adapters, initially I hit at the adapter hub, and then eventually I found the PELT parameter efficient. What does LT stand for? I'm not sure what the LT is. Adapterhub, they actually, so there's two different implementation styles. I'm going to dive a little into the code difference between the two. Functionally, they're kind of achieving the same thing, but this one's going to be a little more code centric this week. Adapterhub starts with the transformer library from Hugging Face, and they did a fork of it, and then they made their modifications to various models within these base models within the transformer library, different base models. And then what you need to do is you will install the transformer adapter library. And when you're instantiating transformers now, this new version has additional methods, and the transformers are similar, but they've been modified. So from a code maintenance perspective, they will frequently do pulls from Hugging Face and propagate their changes forward. And then, you can pull from Adapterhub to include these new changes. The changes to the adapter or to the base models require that you go through in the code and make additions. So like if I had a weight matrix for the key, I have to have this additional weight matrix defined for this model now that's in parallel to that with forward pass that accommodates the addition of that output. We'll look at that a little bit later, but that's the idea then. So both end up implementing the same architecture in the end. One does it by doing a fork of the transformer library and then having changes that they apply to that library, and they just update it frequently. The other library, is it? Yeah, it's not PELT, it's PEFT, parameter efficient fine tuning. Okay, so this one seems to be sponsored by Hugging Face, and it does it a little bit differently, and it uses a language attribute of Python. What they do is they use something where they actually they don't modify the code directly, so they're not changing any of the classes, but what they will do is go in and modify the structures that these libraries are using. So these are all PyTorch neural network modules, and where I might have a module that represents a matrix multiply, a linear layer, something like that, they will essentially take that in the variable that holds that, instead of having it point it to a simple linear layer, they'll replace it with their own layer. And that layer has internally, has both the original linear layer and then the additional low rank matrix next to it. So in the end, it does the same thing, but it does it differently. And it uses an attribute, this dynamic changing of the data structures. I called it monkey patching. When I thought about it, it's not quite monkey patching. Monkey patching is where you go in and you change like functions and stuff like that, or methods in a class. It's not quite that, but you're accessing some of the possibly private member attributes of an object class. Okay. So if you're using transformer adapters from Transformer Hub, you basically have the transformer, the normal transformer, and then you have these adapters. So this is all looking the same. The tokenizer is identical. And now I'm instantiating these adapter model from a pre-trained, and then I add on whichever adapter. In this case, I'm adding on a SST-2. I'm not sure what that is, but you add that to it, and then you set it active. So this BERT adapter model is a different class. It's not a BERT model, it's a BERT adapter model. And it has, it is similar to the BERT model, but it has these extra matrix in it now. Okay, this is contrasted then with a PEFT adapter, or PEFT style, where we're now still using the same original transformer library, transformer model. And what we're doing is importing these methods that will modify the model. So you actually instantiate auto model for sequence to LM from pre-trained. That's just a standard Huggingface transformer model that you load. So model at this point just looks like a standard transformer. When you pass it through this PEFT model from pre-trained, one of the things you pass in is that original model, and then what is the adapter that you're applying to that. So this model now it's like the first one, but it's been modified to include these different implementations of like a linear layer. And once you got it, then you use it in the standard. Here's where tokenizing the input, generating text based on that, and that's all just standard stuff. So the only thing that's different here is where you ran this thing and it modified the Python representation of this structure.
Hey, Roger.
Yeah.
So that third line which you commented out, yeah, right above that, the commented out line.
Yeah.
That's not needed, right? And maybe
Right.
you're experimenting or something.
Yeah, I think that was that would be, that's not needed. I don't recall why I had it in there. Sorry, it's been a little while.
And you have imported PEFT config as well. Did you use that somewhere? You use PEFT model.
I think we're gonna here we're using from pre-trained. I'm going to go through how you would train a PEFT model, and I think we'll use the PEFT config then.
Hey, Roger.
Yeah.
Just a quick comment. I haven't looked at the PEFT library, but if you go back to the previous slide,
Yep.
Where you have the third line in the second block, model equals PEFT model, blah,
Yep.
blah, blah.
Yep.
So you're passing it in your non-adapter vanilla model.
Correct.
Okay. And That's where usually you can also pass in configuration information. So you say comma, RK Stager LoRA, right?
Which is, yep,
I think another way you might be able to call it is something along the lines of
just pass
comma
the,
PEFT config.
yeah, that's probably true if you're changing it, yeah.
Yeah.
This is going to load the pre-trained weights for that. So I don't know if you can change, I don't know which parameters you can change on that, but you might be able to change some of them.
Yeah, my impression is that the various config option objects in Hugging Face, they're basically just kind of like a big dictionary. So
Yep.
you have like a
Like a bunch of,
configuration name and a value, configuration
right.
name and a value, configuration
Yeah.
name and a value. So it's, you know, nothing too fancy or confusing for if you use them for a bit.
Yeah, not much different than keyword arguments, right?
Yeah, and if you go back to the previous slide, just to contrast with the Hugging Face transformers adapter, there you do the same thing.
Whoop. Sorry.
No worries. Yeah. No worries.
Yeah, here you're actually, in this case, you're calling that BERT adapter model. So that is a implementation of a BERT model that has been, somebody's gone in and typed lines of code to change it so that it has this place for adapters to fit in. And then on the load adapter, you're taking a set of pre-trained values and loading that into that place that has been hard-coded in.
Yeah, and my point is just that on this, I'm pretty sure that you could have also said model equals BERT adapter model from pre-trained, BERT based uncased, comma, and given it a config option object that has some keywords and values. So it's just a very standard thing in Hugging Face world that when you instantiate something that you can also pass in a config instead of having to like manually list all the different settings that you want, you can save them into a config option object.
Yeah, possible. That may be true. I don't know.
Yeah, it's just easier. Like imagine that you had 35 settings that you all wanted to override the default behavior. If you have a config object, you can just save that and you can load it versus having to, manually type in 35 different keywords and values.
Yeah. Yeah, I don't know. It's possible. There's actually a different method that's called, right? This load adapter method is being called. So I don't know. I could certainly imagine a config being applied at that level, but I'm not sure. Load adapter, yeah. Anyhow, I don't want to go down this too far, but that you may be right on this. So.
Yeah, thanks, Roger. Yep, but
Sure.
just wanted to kind of reassure people that even if they don't understand the code, like config objects are not really anything too fancy.
Right.
Yeah.
Yep. Okay, so this was the example of how we might train an adapter. So in this case, it's really not, there's very few extra lines of code, right? So we're going to load a model, this big science MT0 large model. We have this file, so get PEFT model here. We have a PEFT config, which is a LoRA config. It did require task type. I'm not quite sure why that affects it, but then it's got a number of parameters that are specific for the LoRA. And then this important part, target modules. So when the PEFT library is going through and like replacing an object, like a linear layer, with this new special linear layer that has both a linear layer and a low rank linear layer next to it. When it's doing that, it does it using, so all of the modules inside of a PyTorch network, let me say, all of the modules have names. And this is using a match on those names to decide whether or not you should convert it from a linear to this low rank linear or not. And so here they're basically saying anywhere you see a Q and a V, replace the linear layer that would be represented by a Q or a V with something that is linear plus low rank next to it. And when you run this get PEFT model, this isn't pre-trained, right? So this is just adding an uninitialized low rank matrix in parallel with the main matrix for all of the modules that happen to match this. And the key difference here is that for the classes that this works for, if you have a new class, all you need to do is identify the names of the weight matrices that are used for light query and value. That's the only change. Once you've done that, then, so if I've got a new model that we've never seen before, I could pass those down for that particular model type. It would modify the model, replacing those matrices. And then it's already, I think it's right when you did the get PEFT model, it's already marked those so that only the new parameters, the new layers are trainable, everything else is not. So you just call the trainer and start training directly. And it's going to train just the new matrix, the new parameters, lightweight parameters. And when you're done, this also save pre-train also knows to just save the new parameters that you've trained. So to create a new adapter is like really easy.
Roger, in this case, it's a LoRa config, so I'm assuming R is the radix and alpha maybe for the, some strategy for zeroing or scaling or whatever, right? And so on and so forth. But what this is a generic library for not just LoRa, but it could be some other configs for prefix tuning, prompt tuning,
Yes.
any of those. Okay.
Yeah. Yeah. And that's where we'll dive into. Okay, so here's model that it already knows. So like the Q and V is T5, it calls it Q and V, whereas in Llama it calls Q projection, V projection, for instance. So it has a bunch of them pre-coded, but you can always pass your own for, if you have something that isn't identified in this already. It'll do these automatically, and then you can do your own. Uh-oh.
Yeah, and just
my
so
screen is messing up.
And we have, I don't know if you've done LoRa in our meetup yet.
You guys still got that screen?
Yeah,
Hello?
I've seen this. Yeah, are you able to hear me?
Can you hear me?
Yeah, I can hear you, Roger.
We can hear you, Roger. I don't know if you can hear us. And I heard Jerry as well.
Okay. Okay, let's see then. I did a little example here. I think especially looking at the time, rather than going through the code, this is what I meant by this monkey patch idea, quote unquote monkey patch.
All right, so yeah, on the left-hand block then is like a normal model and layer. And if you look at the forward method, I just have it printing out forward and multiply by a little weight in there. So when we call the model, the very last line, print m.forward, I'm calling the model forward, and it prints out just that layer forward string with the input X, and then it returns a 2 value because it has a weight of 2. Okay, the monkey patching over on the right-hand side, I have now a new layer that I want to stick in instead of that original layer. So this is like this would be a LoRa linear layer, right? Whereas the first one is just a normal linear layer. This one is going to be an adapter or LoRa linear. When you construct it, it actually will use, it'll pass in. So we have 2 scales now. One is going to be for the the original layer, and one's going to be for this LoRA layer. So you can see that we just it derives from the original layer and adds on functionality. First thing it does is initialize the initial layer, so the original layer, and then it stores away the scaling for the adapter layer. If you look down, see where it says replace module 0. So this is where like the monkey patching would occur. You pass in, you have the adapter layer, the new one that I've created, and then I am updating the old module, or the old m.dot module. So I had previously instantiated module on the left-hand side, and now I'm taking what could be a private member, a private attribute of that module, and I'm updating it now to point to my new adapter layer. And then since adapter layer inherits from layer, I just copy the old module weights into this new adapter layer. And then where you see m.dot module equals new layer, now I've updated the module, the original model, to now use this new adapter layer instead of the original layer. So when I print m.dot forward, you can see that the forward method of my adapter layer calls the superclass forward first, and then it does its own thing with the adapter forward. And so you can see both of those. And in my adapter forward, I said, add to the x times the adapter value. So first you do the normal transformation you do, and then add in the adapter transformation as well. So this is kind of a super simple example of how the PEFT library is changing the objects, the classes, the base classes, to add in the adapter or the LoRA functionality. And as Dave said, this could be different for different types of parameter efficient models that they do. I don't know if that's clear enough for everybody, if anybody wants to dive in or not. I just wanted to provide a simple overview of that. I want to go down, I think, to slide either 31 or 32 now, because I'm going to skip the actual. I had some code that was like dived into the PEFT library to see where they're doing all this stuff, but I think it's, especially given the hiccups we've had, it's not worth doing that right now. These are some of the actual implementations internal. If you go down one more, the base models that Adapterhub versus PEFT uses, they're kind of, similar size. The big difference though is if you want to make a new model in the Adapterhub, you would have to go in and change code on the Adapterhub fork, and it's more lines of code. It's actually from a computer science perspective, I think a cleaner way to make the change, but it's a lot more coding. Whereas if you wanted to add a new model on the PEFT side, assuming it works, assuming the implementation allows you to just swap out one of the modules for this new parameter efficient version of it, then it's just a matter of passing the name of the modules down in as part of that that call that we did, where it made it a PEFT model. Does that make sense?
Yes, it does, Roger. It would also help if you know offhand, or maybe separately, for each of these base models, what all different kinds of fine tuning is supported. Like when I see stable diffusion, it is an ensemble of many models, right? So what does it mean PEFT for stable diffusion, for example? I think that's probably the only one that stands out.
Yeah, I mean, if you know the architecture, you do need to know the architecture. You need to know what the modules are called. But if you do that, you can replace, like in the case of LoRA, you could replace any of those with something that has a fixed, pre-trained version of the matrix, and then in parallel, this this smaller low rank version of it. You do have to know what they're called, and you have to find them. I think you can actually just do a print model. If you print the model out, I think it actually tells you what they are, so you can derive it from that too.
Yeah, so I'm assuming in this case, stable diffusion is just the UNet model, because I'm assuming the encoder decoder is V2GAN, the classifier guidance is through the clip based embeddings. So then it's the cross attention or one of those things that it is probably using it for, or wherever the transform is used. And that's the only place that I recall right now in the overall ensemble.
So one of the things is that the PEFT library only knows how to replace certain types of modules. So linear is one of them. I think there was a 1D CNN that you could also replace. But again, as long as that module is implemented as a named module in that model, then you should be able to just replace it. It knows how to replace linears. Now, what I didn't do, Dave, is I didn't look at any of the prefix, how they handled prefix. I only looked at the LoRA stuff.
No, that's fine. And this is good starting point. Thank you, Roger.
Yeah.
No, I get it.
Yeah. Okay, and then one more, Jerry.
Okay.
Did somebody have a question or comment?
I was gonna respond more to Dave's question, but I can save that for the end.
Okay. Yeah, so we're gonna wrap up here pretty quick then. So the other difference I noticed when I was looking at these two was Adapterhub seemed to be supporting more parameter efficient fine-tuning methods as opposed to the PEFT. So PEFT does do LoRA, which I looked at mostly. It also will do these prefix P-tuning and prompt tuning. I was actually kind of interested in the IA3, which I think we covered last time, where they're really just doing a matrix that scales all of the hidden layers values, and they seem to be claiming pretty good results. PEFT didn't have that. It turns out PEFT now has a pull request for an implementation of an IA3 as well. So they figured out some way to do dynamic, insertion of that IA3 style into models. So I initially, to be honest, I really was not very keen on PEFT because it seemed like bad coding style, but in practical terms, it actually, it adds a lot of value. So, and it's also something that's on Huggingface, is not a whole separate thing. So at this point, I'm kind of feeling like PEFT is probably going to, win out over Adapterhub. My personal call.
Roger, where's Adapterhub?
It is, I think, like adapterhub.something.com.net.
Oh, okay, but it is separate from the Hugging Face libraries then.
Correct. Yes, it's a separate website. Yeah.
Yeah.
I mean,
okay. Yeah, I think you're right then.
It's a great vision. This idea that I can just add, this incremental capability. But I just think it's going to be better implemented inside of Hugging Face. And the technique Hugging Face has chosen is very flexible, not as clean, but very flexible.
Okay, thank you.
Okay, do we have, I think what's the next slide?
There's one more and then a thank you.
Thank you, yeah. Oh, this was just the types of changes that you do if you were doing a Hugging Face style. You can see you'd have to go in and find the BERT self-attention and make that modification where it says linear. You would plug in something called LoRA linear. Not a big change, but it does require going inside and modifying the code, and it requires keeping a separate fork.
Okay.
So, okay, that was it. I was going to go through the QLoRa, but we're not going to have enough time. Just the teaser for that is that they essentially use the LoRA technique to run. They have a large model that they instantiate pre-trained model that they instantiate in very highly quantized implementations. So instead of 32-bit floats, they use 4-bit. It's quantized down to 4 bits. You get a lot of loss when you do that. The model quality goes down. They add LoRA next to it in 16-bit and train it, and you can do, I think they said in a single GPU in 24 hours you can train it, and it's back up to the original values, basically the original quality, and you can train it, on a specific task, and you can do that on one quote unquote consumer grade GPU.
Does this also let you deploy that model then to, something with kind of weak, like a Raspberry Pi or something like that?
Well, I don't know Raspberry Pi. What it means is, you can take a 65 billion parameter model, and by implementing it, instead of just in 16 or 32-bit floats, you can implement it in this hybrid where a bunch of the parameters are 4-bit and a few of the parameters are 16-bit, and you can get comparable quality. It's not just 4-bit during training. It's 4-bit during inference.
Yeah. Okay, but you're using the quantization and the full 16-bit, if you want to call 16-bit full.
Yes. Yeah. You kind of add those two together, and somehow magic happens, and you get you're predicting similar results.
Very interesting.
Yeah. So yeah, I'm not going to do that now. If people are interested, we can probably fill up at least half of another meetup sometime on that.
Okay.
I'll just end here.
And if you notice, or if you recall, there was Q and V layers that were being modified. That was highlighted by Roger. So in any transformer, that is the biggest operation, right? A multiplication of Q and V vectors across all tokens. So quantizing those before you do that operation saves a lot of parameter space and the operation space and time and everything. So yeah, that's
there's one slide, if you can go down a little here, that was kind of interesting. There's a coding example somewhere. Keep going. It was amazing that the Hugging Face libraries now, what's the one just before that then? Oh, did it not make it in? Oh, wait, no, the one in between, just above thank you.
Oh, just above thank you?
No. Yeah, look at that. Load the model, pre-trained model, load in 4-bit equals true. That's all you need to do. Wow, that's
probably a lot going on behind the scenes, but from the developer endpoint, it's trivial.
But pretty interesting that with the Hugging Face libraries, yeah, you can get a 4-bit implementation of a model just that simple.
So this is loading in, I guess, something from Facebook, what, 350 million parameter type deal or something like that?
Cut and paste on my part. I don't know what it is, but
yeah. Okay. And just doing this, it'll give you the model back with 4-bit. Huh.
Right. And then we could then use PEFT to add our 16-bit LoRA in parallel with all that model, and then train it for 24 hours, and you've got this amazing model in a very small amount. It's if you look at the leaderboard, that's it was doing pretty good, at least with respect to the open source ones. So anyhow,
so Jerry, couple of quick points on what you asked, right? So one is for QLoRa, for example, yeah, it's a single line, but there's a lot going behind the scenes, and I think it's more or less the PhD thesis of the person who came out with QLoRa, including a new 4-bit data type, so which is not part of the typical data type that you will see in the language, and
I'm seeing that 4-bit quantization referenced quite a bit in a number of papers. So it must be, I don't know if it's the same guy or what, but it is.
So quantization as such, and that was the second point I was going to make, that quantization as such is very important for mobile models, and a lot of work has gone in both at Google and Apple to come up with squeezing or putting in many kinds of different optimization compression tricks, including quantization. So quantization is one of those, but there are many more that they just put all together to get the comparably good or reasonably good result. And 4 bits may have been done there, but this QLoRa specifically is combination of LoRa and 4-bit quantization with a new data type. The previous 4 bits are using the vanilla int 4 bits, but this one is, if I'm not mistaken, it's a newer data type that they introduced.
Yeah, and I just wanted to say that I was very confused when I heard people talking about 4-bit arithmetic. And so like, you know, an 8-bit integers, 8 bits, right? A 4-bit integers, 4 bits. When they're talking about 16-bit floating points, my understanding is the entire floating point number fits in 16 bits, okay? But when they're talking about 4-bit floats, what they really mean is a 4-bit mantissa. And so it actually takes up more than 4 bits. It takes like 7 bits or something like that.
No, actually, my computer messed up some. Actually, Ted, when we were talking about 4-bit in this context, this is a quantized 4-bit. And so it is a storage 4-bit. They use 16-bit for all operations. All math is done in 16-bit. But when they store it, it's quantized and stored in 4 bits.
Okay, because I know that there's inference where it actually does the inference on less than 16-bit numbers.
Okay, it might be a different one than the QLoRa, at least, is using a quantized 4-bit storage and using, whenever you do any operation, you'll expand it to 16 bits, dequantize it, and do the multiplication.
Okay,
but it's stored in 4.
Yeah, and then if that's the case, then they're using 4-bit integers, unsigned integers probably, for those. But there is 4-bit floating point numbers out there. Like if you look at Tim Detmer's bits and bytes and whatnot, and those, when he says 4-bit float, he means 4-bit mantissa.